Hi, myself Naveen Kumar Saini. In the course of electromagnetic field theory, today we are going to discuss in continuation of electrostatic fields. In this, we will take one of the very important topic in electromagnetic field theory. This is boundary conditions. So we must know what is the boundary condition and what is the significance of this. After that, we will derive the boundary conditions. So in that, boundary condition means when we have the two mediums. So till now we have discussed about the one medium in which we found the force between the forces and then electric field into the any field. So we calculated that. Now the case is when we have the two mediums, so medium 1 and the medium 2. So these two mediums are like that, and what we want the condition between these two mediums, okay, at the interface. So at the interface or at the boundary. So for that one, so what it shows that when we know the electric field into the one medium, then we have to find the electric field into the second medium when it is reflected into the next medium, right, or the reflected into the next medium. So if we know the electric field into the second medium, then we can calculate the electric field into the first medium, so and so vice versa. So there are basically three cases are there which we are going to discuss about the boundary conditions. So first case is the dielectric interface. So it means the one medium is of one dielectric, second medium is of second dielectric, okay, or the different materials. So this is the first case, or we can say this is the general case as well. Second one is the conductor dielectric. So one medium will be the conductor and second medium will be the dielectric. Third case is the conductor and the free space. So for solving all these three cases, we will use a Maxwell's two equations in the integral form. First one is E dot dl, which is a closed path, right? So this is the closed path. E dot dl is equal to 0. And second one is the D dot ds with the closed surface is equal to charge enclosed. Okay. So as we are aware about this, then what is that? From this equation, which Maxwell equation we obtained? We obtained the del cross of E is equal to 0. And from this equation, we got the del dot D that is equal to rho into V. So these are the well-known point Maxwell's equation, del cross E is equal to 0 and the del dot D is equal to rho V, right? Total charge enclosed. So these two equations we will use these two equations for solving the boundary conditions. So the first case which we are going to discuss about the dielectric case. In the dielectric case, we are assuming that the above medium is the medium number 1 and below medium is the medium number 2. So medium number 1 is defined as the epsilon 1 and medium number 2 is defined by the epsilon 2. So these are the two mediums. So epsilon 1, which is one of dielectric, epsilon 2 for the second dielectric. So for that we are finding that electric field into the medium 2, this is the E2, right, and it is passing through this interface and it is going out into the medium number 1, right. So what we want what is the condition, how the electric field will change when at the interface, right. So this is nothing but this is the at interface. Okay. So next step what we are doing, we are just simply converting the E2 and E1, or we are bifurcating into the tangential and the normal component. So for that one, what we have, E1 that is equal to E1t plus E1n. So we can see E1 is this one and its two components, tangential component is E1t and the normal component is E1n. So this is E1, right. Similar to that, we have the E2 that is equal to E2t plus E2n. So this is the second equation. So we can see it here. So for this E2, this is the electric field, total electric field in the medium 2. So we are bifurcating into into two components. First one is the E2t. So this is the parallel component to the interface or the tangential to the interface, and E2n, this is a normal component of towards the interface again. So E1, that is E1 is equal to E1t plus E1n, E2 is equal to E2t plus E2n, right? So we will use these two equations, right? So in now next is what we want the boundary condition at the interface. So what is the first equation which we have? We have the equation that is your closed is a closed path E dot dl is equal to 0, right? E dot dl is equal to 0. So it means this is the multiplication between the E and dl. So dl is the length and E is the electric field in the mediums. So for that one, what we are doing, we are simply covering this interface. So this is the interface this is the interface, and we are covering it with the closed path A to B, B to C, C to D, D to A. So this is the direction for the closed path. So we have to integrate this E into dl. So for that one, just for example, we can take it here, right? So apply this E dot dl. So E dot dl means this is equivalent to A to B E dot dl plus B to C E dot dl plus C to D E dot dl plus D to A E dot dl, right? So this is nothing equivalent to the closed path E dot dl. I hope this point is clear to all of you. Now just apply this from A to B. So this is A, this is B. So A to B, this is the path whose length or width is delta W, and B to C whose height is delta H, right? So this is nothing but the path, right, which we are following. So A to B, when we are moving, so what is the electric field? So this is the electric field. This is A to B is in the medium 1. So corresponding to that electric field is E1t in the medium 1. So E1t into delta W. So both are in the same direction. So this is the positive, this is a positive thing which we will get it. So very simply we can write it for this case. A to B is the this is nothing but this is the E1t into delta W plus now B to C. B to C, in the B to C, first half of this one is in the medium 1 and second half is in the medium 2. So in this case B to C, when we are applying, B to C means delta H by 2, and electric field direction is E1n. This is normal, but this is the opposite direction. So this will be nothing but E1n into minus delta H by 2. Similar to that, for this case, second half electric field is this one. So this is upward, and B to C, second half of B to C is downward. So again it is with the minus sign. So we can write as the E2n minus delta H by 2. Okay. Now come to the C to D. So C to D will be what? In this direction, and for this one C to D, right? C to D is in the medium 2. So in this case we can say this is the E2t with the minus sign. So it will be minus of E2t into delta W and so on, plus we can write for this case D2A. D2A first half is in the medium 2 and second half is in the medium 1. So I am writing here only. So in this case D2A, right? So for the D2A, it will be D2A means E2n into delta H by 2. So both are in the same direction, right? I am writing this one, this portion here, right? Plus in the second half E1n into delta H by 2. So in this, that is equal to, total is equal to 0. So in this case we can see it here. So E dot dl, that is equal to 0, and this is E1t delta W and minus E1n delta H by 2, E2n delta H by 2 again, minus E2t delta W and E2n delta H by 2 and E1n delta H by 2, right? So in this case we can see that this will cancel out here with the minus sign. So this what left? So what left? This is the E1t delta W is equal to minus E2t delta W is equal to 0. So this is the equation which we got it. So this equation is from A, B, C, D, A, right? So this was the path A, B, C, D, A. So important point in this case is only this one, when we are moving from B to C or we are moving from D to A. In this direction, the electric field will be changed, because in the below medium it is the electric field 2 and above one it is the electric field 1. Okay. So in this case, when we are solving this, because delta W cannot be 0, so that is why E1t will be equal to E2t. So the statement for this E1t is equal to E2t is tangential component of electric field intensity is continuous at the interface, right? At the interface. So we have to mention it at the boundary or at the interface, right? So one way is we are solving this. Second way is directly we can put delta H tends to 0. Both are same thing, because when the delta H tends to 0, it means delta H tends to 0 means we are talking about the at the interface or at the boundary. Okay. So tangential component of E are equal at the boundary or the continuous at the boundary. ET undergoes no change on the boundary and it is continuous across the boundary. So this is very important statement for this expression E1t is equal to E2t. Okay. Okay. So now second case. Okay. So as I said about the E1t is equal to E2t. So we can define it in terms of the electric flux density. So simply we can write it E1t divided by epsilon 1 D2t divided by epsilon 2. So in this case, when we are solving this, then we are getting this expression epsilon 2 d1t is equal to epsilon 1 d2t. So what it says, the electric flux density is discontinuous at the interface, right? But here this is a tangential component, so we have to specify in correct order that is discontinuous across the boundary, or tangential component of electric flux density is discontinuous at the boundary or at the interface. So I hope this point is clear to all of you. So this is the electric field and electric flux density tangential component. So now we will talk about the normal component, right? Normal component which can be applied by using the Gauss law, and this Gauss law gives a Maxwell's second equation. So for that, what the availability which we have? This is the case when we have the D2 is moving in this direction, D1n is moving into direction. So why we are taking the D, not the E? Why? Because in the Maxwell's first equation, we have taken E dot dl, so that is why we have taken the electric field in this case, right? So now we have the Maxwell's second equation which is coming from the Gauss law, that is D dot ds. So that is why we are taking the D here, right? So D2 is in this the medium 2, corresponding to that D1 is in the medium 1. So again we will bifurcate into the two components of the D. So D2 is two components are bifurcating, D2t plus D2n. So we can write it here. So D2 will be equal to, we can write D2t plus D2n. Similarly, we can write the D1, that is D1t plus D1n, right? So this is the bifurcation of that these two components. Now, so as we have divided this D, now we will talk about the ds. So ds is what? A surface along the interface. So in this case we can see, so here we have, this is the one pillbox in which this is the surface like this is a delta S surface. So this surface will covering this surface area of the interface. So if you are integrating this complete interface, then we can get the d dot ds, right? And second point in that is the charge enclosed. So here we can see at this location, so how much charge is enclosed by this given pillbox, that is defined by the d dot ds. So we will apply this case here. Again at the interface we have to take the delta H tends to 0. So we have to take it. So I hope this point is clear. So now apply this. So in this way, this is the D1n, this is our delta S and D2N. This must be like this, right? Then only we can multiply. And we are assuming we can find out that there is no direction D in the tangential component into the interface, right? So for that one, what we are doing, we are applying the D1N into delta S. So we can see D1N is in this direction, delta is again in the same direction. The both directions we have the D1N and the delta S. So this is the D1N delta S in the same direction, that is why we are taking the positive sign. Next is D2N into delta S. So we can see D2 delta S is again in the, this will be downward perpendicular to the surface, and D2N this one. So we can see here that D2N is the opposite direction of the delta S. So it means if it is the opposite direction, then in this case when we multiply these two components, then we will get the D2N delta S with the minus sign. So D1N delta S minus D2N delta S is equal to charge enclosed. So this charge enclosed on this surface. So for that one, what we have? We have the surface charge density. So here the surface charge density is the this is rho S coulomb per meter square, right? So this is the coulomb per meter square surface charge density. So how can we write the delta Q? So delta Q we can write as the rho S into delta S. So we know the formula for that. Okay, if we want delta Q, right? So we know the Q, how we calculate the total charge onto this. This is the rho S into ds, right? So this formula, I hope each one of you are aware about that. Okay, so when we integrate this or differentiate this, then we will get the rho S, delta Q is equal to rho S into delta S, right? So in this equation, delta S cannot be 0. So because if surface is 0, so it means it become the point. So it cannot be 0. So that is why we are taking the D1N minus D2N is equal to delta Q or rho S, right? So delta S can be cancelled out here. But if we are assuming that delta S can be 0 or not, so delta S cannot be 0. So as I said, if delta S is 0, it means there is a point. But if it is a point, then there is no point of the interface or the boundary. So boundary can be calculated when, or assuming when we have the delta S which has some value. So it cannot be 0. So expression which we can get it, that is D1N minus D2N is equal to rho S. So this is very important feature, important expression which we got for the normal component. Okay, so now we have a special case in that. What is that? So we are assuming when the region is charge free. So we are assuming at this region there is no charge present. If at the interface no charge is present, in this case rho S will be equal to 0. There is no surface charge, so surface charge is not there. So when rho S is 0, then the expression which we got, that is D1N is equal to D2N, right? So this is the D1N is equal to D2N. So we can say that the normal component of electric flux density is continuous at the interface. And when we are converting it in terms of electric field, then we will get this type of expression. Simply just put D is equal to epsilon. We know this formula. D is equal to epsilon naught into E, right? Because there is no free space, so we are taking the epsilon only, right? We will take the epsilon. So epsilon E, just put it and we will get this expression. So the statement for this is what? This is the normal component of electric field intensity is discontinuous at the interface when rho S is equal to 0, when there is no charge present at the interface. Now this is the third part of the first general case, right? First one is a tangential component, second is a normal component, third one is a law of refraction. So for that one, we are taking this diagram here. We are combining both the cases of D and E. So here the D2 and E2 is in the same direction, D1 and here E1 and D1 is in the same direction. So again we can bifurcate into two components. D2 will be D2T and D2N. E2 will be E2T and E2N. So these are two components, right? Again, if for the electric field E1 we have the E1T and E1N. For D1 we have the E1T into ED1N. So this is the angle. Theta 2 is the angle for the incident, and alpha 1, theta 1 is the angle for the refraction in the second medium. So for this case again we will use this E1t and E2t. So we can see it here. E1t is this one, this is the theta 1, this is theta 1, so this is E1. So what is this expression? So E1t is equal to E1 cos of, sorry, E1t sine of theta 1. Okay, so on E1n, so here E1n will be equal to E1 sine theta 1, sine E1n. So this will be cos, sorry for this, so it will be a cosine. So I will explain again. Okay, so here base value will be your, so E1t, that is your E1 sine theta 1, and here E1n will be equal to E1 cosine theta 1. Similar to that for the D1t, D2t, D1n. Then similarly we can find for the E2n, D2n, E2t and D2t. So when you apply all this all together, then E1t, E1 sin theta 1, E2t, E2 sin theta 2. Second expression which we have D1n and D2n. So for that D1 cos theta 1 and D2 cos theta 2. So just simply take D1 is epsilon E1, D2 is epsilon to E2. So just divide equation number 1 with the 2. Then when we divide these two equations, then automatically when you're solving, and in this case, then we will get the tan theta 1 upon tan theta 2 is equal to epsilon 1 upon epsilon 2, right? So we can convert epsilon with the epsilon naught into epsilon r. So this will be epsilon r1 upon epsilon r2. So here we got the tan theta 1 upon tan theta 2 is equal to epsilon r1 upon epsilon r2. So this is nothing but the law of refraction. So till this point we have to prove the dielectric case. So as again I am repeating, 3 cases are there, 3 steps are there to resolve complete expression: tangential component, normal component for electric field, and the electric field intensity and electric flux density, and third is the your law of refraction. So this up to this expression you have to solve for the dielectric case. So now we can have the second case. This is the conductor dielectric case or dielectric boundary condition. So we have to find the same expression we have to write, and same method which we applied for the dielectric case. So we have to apply it here, right? So the case is conductor and dielectric. It means in the previous case we have the dielectric, then the dielectric, and interface between these two surfaces we found the boundary condition. Now in place of below one we have the conductor. So we must know some of the property of the conductor, then we can easily solve this type of questions. For the conductor, within the conductor we are aware that electric field is 0. So what is the significance of that in the conductors? So when you put the conductor into the external electric field, then the charges, positive charges will be into the same direction of electric field, and negative charges will be opposite direction of the electric field. So in that case what happens, within the surface there is no charges present into the electric field, there is no charge density within the conductor. When there is no charge density within the conductor, there is no potential, and then there is no electric field within the conductor. So that is why they have mentioned the electric field here is the 0. So electric field is 0 in the conductor, so we have to find the electric field in the dielectric. So same procedure we have to apply here. So here the equation which is mentioned here, that is nothing but the E dot dl is equal to 0. So apply this equation to the path. That path is again the same, A, B, C, D, right? So delta W is the width of this path, and delta H is nothing but this is the your height of this path, right? So when we apply this equation, E dot dl is equal to 0. So again we can see if we are moving from A to B, so in this case what is the E dot dl? E is in this direction, En, dl Et is in this direction, and A to B is the same direction. So we can have the Et into delta W for this case. Okay, so for this case again we have to take the two parts. So first one is En minus sign into delta H by 2. This is the case into the in the first medium. In the second medium, in this direction E is 0, so we can take 0 into delta H by 2, right? So this is in this direction. So is the electric field. Now come to C to D, because electric field is 0. So what is the E dot dl? So here E is 0, dl is delta W, right? 0 into delta W, that is 0. This is also 0, so the plus sign I can write. Now come to D to A. So for this case, D to A, again this first half and the second half. First half is in the medium 2, or you can say in the conductor medium, and second half is in the medium 1 or in the above medium. So when you apply E dot dl here, so for this half, what is E? E is 0 into delta H by 2, right? And for this case, because here electric field is the En, so we can write En into delta H by 2, right? So when you add all this Et into delta W, when you add En into delta H by 2, 0 into delta H by 2, 0 into delta W by 2, also delta W, here 0 into delta H by 2, and then En into delta H by 2. So automatically when you add all these things, then the equation maybe looks like this, right? So when you're adding all these things, then we can see easily that here that En delta H by 2 will cancel out to En delta H by 2. Okay. So this is 0, no issues with this. This is 0, no issues with this. This is also 0, no issues with this. So what we have? We have the Et into delta W is equal to 0. So delta W cannot be 0. So we can write the Et is equal to 0. So electric field, tangential component of electric field is 0 in the above medium, in the dielectric. So we can convert in terms of D. So dt is also 0. So electric flux density, tangential component of electric flux density is also 0. Okay. So here we can find this, how we are getting. So here we can see that this is the same expression dt or Et, that dt and Et. So we can find all these things. Okay. I hope this point is clear to all of you, how to get this expression. dt and Et is 0. Now second point in that is the conductor dielectric case. When we have the surfaces, what is this is Gauss law, d dot ds is equal to 0. This is also very simple. So we can see here, again we can take the one of the pillbox for that. In the above medium we have a dn, in the below medium, because this is a conductor, electric field is 0, right? Apply the d dot ds. So for this case, d dot ds, d is dn into ds, this is delta s, right? Now come to for this case, delta s is this one, right? dn is not there because electric field is 0, it means the electric flux density is also 0. So here d dot dn will be 0 into delta s. Okay, delta h tends to 0, we have to take at the interface. So when we are applying this all together, then we will get dn into delta s minus 0, delta s is equal to delta q. Okay, so delta q is nothing but the charge enclosed, delta 2 is nothing but the charge enclosed. So in this case, dn will be equal to delta q upon delta s. So delta dn is equal to delta q upon delta s. So this is the expression which we got, right? So dn is equal to delta q upon delta s. So we can solve it further. Delta q is what? Delta q is nothing but rho s into delta s divided by delta s, right? So dn will be what? When you are solving, then delta s will be cancelled out, dn will be equal to rho s. So this is the case for the boundary conditions for normal component. If we apply the Gauss law, then dn will be equal to rho s. Okay, so dn is rho s, so we can say the special case when rho s is equal to 0. So when the rho s is equal to 0, it means dn is equal to 0. It means the normal component of electric flux density is equal to rho s. If rho s is 0, then dn is also 0. Okay. So, but important point is to measure, that is the delta H. So, delta H tends to 0. So, in the conductor dielectric boundary conditions, there are some of the points which we must be aware. First is no electric field exists inside the conductor. Second, electric field is equal to minus del V, right. So, this was the first case. This is the second case, E is equal to minus del V. So, E is equal to minus gradient of V. So, it means there is no potential difference between any 2 points in the conductor, right. Third point in that, the electric field must be the external to the conductor, right, must to the conductor and must be normal to its surface. Okay, this point must be clear to all of you. Okay, so this is the last case, conductor or free space boundary condition, in which there is nothing to change, simply conductor is the same case, but in place of epsilon we have to put the, here this is nothing but, if this is epsilon 1, so okay, so if epsilon is equal to epsilon naught into epsilon r, right. So epsilon r will be 1, so in this case dn will be equal to rho s, and as in the case earlier, dt is equal to epsilon naught et. So this is the expressions which we got. dn is equal to nothing but epsilon naught en, that is rho s, or dt is equal to epsilon naught et into 0. So these are the three cases which we have covered. Okay, first is dielectric case, second conductant dielectric case, and third is a conductant free space case. So I hope this point, this is very important topic, and if you found any difficulty, please you can write to me. Okay, thank you very much.